Today we are solving linear systems, and some of our systems might have some unusual solutions, as in having no solution or infinitely many solutions. In example one, it says solve the system of equations using any method. Now, because this first equation is solve for y, we've got y all by itself. The most efficient method would be substitution. So we would take the 2x minus 8 that equals y and substitute that for y in the other equation. So when I'm substituting in, I like to first write the equation as it was, 6x minus 3y, but instead of y, I put a blank set of parentheses, and then inside the parentheses, we put the 2x minus 8. The next step would be to distribute that minus 3, making sure we distribute that negative sign along with it. So after distributing, we have 6x minus 6x plus 24 equals negative 3. Remember, when you take a negative times a negative, it is a positive. Then we would combine like terms. 6x minus 6x is 0x, so there's no x left. That leaves us with 24 equals negative 3, which is obviously a false statement. 24 does not equal negative 3. So there is no solution. If we were to graph these two lines, they would be parallel lines. They do not intersect. In example 2, again, this first equation is solved for y, so it makes it a good candidate for substitution. So I would take the expression that is equal to y and replace that expression, replace the y with that in the other equation. First, I like to write the equation as it was, but instead of y, I put a blank set of parentheses. And then in the parentheses, we're going to put the negative 1/3 x plus 7. Next, we will distribute the 3. We're going to take 3 times negative 1/3 x, which gives us negative 1x, and 3 times 7 gives us 21. Combining like terms, x minus x is 0. We're left with 21 equals 21, which is a true statement, and there's no variable anymore. There's infinitely many solutions, so these would be coinciding lines. The lines would intersect infinitely many times because they're actually equivalent equations. Any xy pair that satisfies the first equation also satisfies the second equation. In number 3, I would solve this one by elimination because both equations are in standard form. So this bottom, I'm looking at the x coefficient here. This one is negative 6. So I would like the other one to be a positive 6 because the goal with elimination is to get coefficients that are opposite. So to go from 3 to 6, I would be multiplying by 2. And I'm going to multiply all of both sides by 2. So my new equation is 6x plus 12y equals negative 8. The bottom equation, we're not going to change at all, just rewrite it. And now we will add these equations together. So 6x plus negative 6x is 0. 12y plus negative 12y is 0. And then on the right-hand side, negative 8 plus 8 is 0. So we're ending up with 0 equals 0, which is true. So just like before, if the variable's gone, but you're left with a true statement, there's infinitely many solutions, and those lines are coinciding. Example 4, I would want to solve this with elimination again, because both equations are in standard form. If this is a 15x, we want this one to be a negative 15x, so I'm going to multiply the top equation by negative 3. So the new equation, after multiplying everything by negative 3, is negative 15x plus 9y equals negative 51. The bottom equation, I'm not going to change, so I'm just going to rewrite it below the other one. And then when we add these equations together, our x's add out, and also the y's add out. So we're left with 0 on the left-hand side. And then on the right-hand side, we have negative 51 plus 44, which gives us negative 7. 0 does not equal negative 7. So the variables were gone, and we were left with a false statement. That means there is no solution and that these are parallel lines. Solving this system of equations by graphing. My first line, y equals 1/4 x minus 5. Conveniently, it's in slope-intercept form, so that makes it easy for graphing. We'd start by plotting the y-intercept, the 0, -5, and then from there I'd go up 1, right 4, up 1, right 4, and then I would connect those points with a straight edge. The second equation is in standard form, so I would the quickest and easiest way to graph it when it's in standard form is by finding the x and y intercepts. So I put 0 in for x. So -3 times 0 is 0. That leaves us with 12y equals 24. I would divide both sides by 12 and I get y equals 2. So 0, 2 is 1 point that is on this line. I would plot that. And then finding the x-intercept by putting 0 in for y. 12 times 0 is 0, so that leaves us with -3x equals 24. Dividing both sides by -3, we get x equals -8. So then I'm going to plot -8, 0, and connect those points with a straight edge. You can see here I'm going up 2 over 8, which is a slope of 1/4, and over here we're going up 1 over 4, also a slope of 1/4. So these lines are parallel. That means they'll never intersect. So there is no solution that would satisfy both of these equations. So that has no solution. We have parallel lines. Number 6, graphing the first one, I would find the x and y intercepts. So I'm going to put 0 in for x, which leaves us with 3y equals 12. Divide by 3, we get y equals 4. So I'm going to plot 0, 4. And then putting 0 in for y leaves us with 2x equals 12. Divide by 2, we get x equals 6. So I'm going to plot 6, 0, and connect those with a straight edge. Next, the bottom equation is in slope-intercept form, which makes it convenient for graphing. So I'd start by graphing the y-intercept of 0, 4. And then from there, go down 2, right 3, down 2, right 3. You can see we're going right over the top of that previous line. So there are infinitely many solutions. So any xy pair that satisfies the first equation also satisfies the second equation. They are coinciding lines, and there's infinitely many solutions. So to recap, anytime there's an unusual solution, both will start by having no variable. But if you have no variable and a true statement, then it's infinitely many solutions and coinciding lines. If there's no variable, but you have a false statement, then there's no solution and you have parallel lines.